We'll start in 3, 2, 1. Hi, everybody. Welcome. It's Circuits again, back in Burchard 118. I'm so happy you're here. We have a sold-out audience tonight. Thanks, everybody. Listen, this is your time. I want to help you. That's why I'm here. Ask questions because the home audience cannot. So if you have a question, since there's 450 plus colleagues in these sections, I can guarantee you someone else has a question. Now, first things first, let's make sure we know exactly what's on the exam. All right? So, here's the game plan for tonight and also to let you know what is on the exam. So, first topic, second order systems. So, or second order circuits, however you want to call it. This is going to be a second order Diffie-Q. I'm going to ask you to solve it. We're going to look at it. We have two examples we're going to look at tonight. Okay? You might remember, and if not, it's okay. There's only two ways that I know of to easily ask you this question. I can ask you for the voltage across the capacitor, or I can ask you for the current. I thought we'd do it both ways tonight. So you got it all on film, and you can see the whole thing over and over, however many times you want to watch it. Now, next step, sinusoidal steady state. If you don't mind, I'm going to use the EE acronym, SSS. Sinusoidal steady state. Now, there's probably going to be two problems on this. Okay, don't hold me to it, but that's my guess. Now, on the screen here, excuse me, we're filming this on Monday night, November 11th. We have gone through example 5.4. We went through that today, which was the basic circuit analysis using a ZEQ. And we also went through example 5.5, which got into voltage division and another ZEQ. So we're not going to go over these again tonight. I went over them in class. But I'm putting them down as a reminder. You should know how to do, Zach, that was 5.4 and 5.5? In fact, my colleagues, I forgot the most important part. Zach is our colleague. He volunteers his time for SITTV. He's done this now. This is at least his third time. Zach, we wouldn't be able to do this without you. Thank you very much, Zach. Appreciate it. All right. So, my colleagues, you should know examples 5.4 and 5.5. Now, what else should you know? You should know how to do nodal. Now, for those of you here in the live audience, we haven't done nodal yet. That's going to be Wednesday's lecture. You're going to see it tonight. Okay? So I'm going to give you the heads up. So you're going to see nodal tonight. The other example is mesh. Okay? What I want to do is one of the examples in our lecture notes, which you'll also see on Wednesday, but you'll see it twice, which I think is a good thing. So, my colleagues, this is what I think as of now the exam will have. A second order system, and the examples we looked at in class, one was, I thought, basic, a series circuit. The other was a little more complicated with the ZEQ in parallel and voltage division. Then we have nodal and mesh, which is the next step up. Okay? So, as of now, I'm thinking there's one question on this, and there's two questions from here. What we're going to do tonight is two problems on second order systems. No sense doing the examples. I did them today. We'll do the nodal and the mesh. Okay, so those are the four problems. Now, I'm expecting a lot of emails Sunday night, which will make me a little sad. People will ask me, is AC power on the exam? For those of you who were in class today, what's the answer? No. Okay, so you're going to see questions on exam 3 with AC power. It's not on the exam. Please don't send me an email, okay, asking that question. Now, the other thing we need to be careful about, I've adjusted my pace in this course. You'll have to let me know at the end of the semester what you thought. I've slowed down a little bit to make sure that we can absorb the important information. So some of the material tonight is on previous exam 3s, but some of the material tonight is on previous exam 2s. Okay, so you need to look at exam 2s and exam 3s. And again, you're going to see questions on exam 3. For example, on AC power, there's a bunch of questions on filters. That's coming up next. Okay, so let's go through these 4 problems: 2 second order, a nodal, and a mesh. And that, coupled with today's lecture, I think you got the foundation. Does the game plan sound okay? All right, good. Let's do it. All right. So, all right. So the first exam I'd like to look at is quiz 2. Okay. Quiz 2 from the spring of this year. All right. So quiz 2, spring 2019. And if I slide down, it says maximum power transfer analysis of a first order circuit, done and dusted. We've had that on previous exams. It's problem 3 that I want. Okay? So problem 3, analysis of a second order system. So what I'm going to look at is problem 3. Okay? So easy circuit to copy. While you're erasing, while you're copying, I'll erase. All right. Now, some of you, will hopefully remember all of this. Maybe all of you might remember all of this. So it says here, you got this circuit. The switch has been open for a long time, and V sub A is the DC source. Okay? Now, it says, write the second order differential equation in standard form. Now, a note about the formula sheet. I'll give you the second order formula sheet, which you'll probably find on exam 2. All right. So write the second order differential equation. Here is the key phrase for the capacitor voltage. That's very important you read that. For the capacitor voltage. The only variable that should appear in your standard form should be V sub C of t. Okay? Now, you might remember I said in this course, when we encounter a second order circuit, we always take a walk. So whether I ask you for the voltage or the current, take a walk. Okay? So I put an X. Now, that's not on the exam, that's on the solutions. So I put an X and we close the switch. And, let's go through this together because it's been a couple of weeks since we've done this, I think. Minus Vs plus, now remember, when we take a walk, everything is voltage. So, VA, sorry. Wow, our audience is live and wired and set up. I love it. V sub A, and then it's R times I of t plus L. Sorry to have my back to you, my colleagues. Doesn't look good on camera, but that's life, I guess. I'm sorry. Plus L di dt plus V sub C of t equals 0. So that's the first step. We write the equation. Now, this equation bothers me because I clearly stated in the problem I only want V sub C of t. I got I of t. All right? But I noticed that I of t, that I goes through the capacitor. So what must be true? I equals C dV dt. So what I now want to do is to do a substitution of variables. So I'm going to assume you can do this in your head, and you're going to stop me if you can't. I'm going to start with the derivative term, L. Now, what's di dt? Exactly. Derivative of this. Derivative of this, which would be C. Aha. This is where we get the second derivative. What I did was I took I of t and I put it in here, and I had to take the derivative. Second derivative. Now, plus r times I. I got to get rid of the I. So that becomes R C dVc dt plus V sub c of t equals VA. Let me stop. How we doing? Okay. All right, good. Now, next step, put it into standard form. Now, I mentioned what standard form is on the answer key, but I bet you know it here. What is standard form? Princeton. Princeton, very good. You got it in one. Coefficient of the second derivative term is 1. Okay. So I'm now going to divide through by LC. Okay. So what I get is the second derivative plus RC divided by LC, R over L, times the derivative of C dt plus 1 over LC times V sub c of t equals VA over LC. Okay? That should be the answer to A. So let's slide down. Okay, so I'm back on the screen. And we got it. I think we're off to a good start. What do you think? All right, good. All right, let's go on to part B. So part B says, all right, you are now given that the second order circuit is overdamped. Help me out. What does that mean? Overdamped. Yes. Close. Zeta is greater than 1. Zeta equals 1 is the break point. Zeta greater than 1, overdamped. Zeta less than 1, underdamped. Okay. Zeta equals 1, critically damped. So what we have is the case where this circuit is overdamped. It says here, I also give you 2 initial conditions. Determine the complete solution. Now, I'm going to leave this equation up here if I can, because I'm going to need it. Let me get rid of this. Maybe I won't need it. Well, we'll keep it there anyway. Now, my colleagues, we want the complete solution. By me telling you it's overdamped, I'm telling you the homogeneous solution. So you go to the formula sheet, which you'll see at the back of the exam, and the homogeneous solution, V sub c of t, for overdamped is K1 e to the S1t plus K2 e to the S2t. That's the homogeneous. Now, I'm not done yet. That's only part of the solution. What's the other solution? Exactly, the particular. Now, please don't fall into this trap. First order, the particular was the right-hand side. That's not always the case here. But what is always the case, let me just write it down here. V sub c particular is a constant. Now, why do I know that's true? Because the input's a constant. Okay? The particular takes on the form of the input. So the particular is a constant because the input's a constant. So I say, all right, I already have K1, I have K2, let's call this K3. Now, just to pick a variable. Now, I'm glad I kept this equation up here. This is a solution to this second order differential equation. So I can take K and I can put it in wherever I see V sub C of t. Second derivative of a constant. First derivative of a constant. What do I have? 1 over LC times K3 equals VA over LC. What's the particular solution? VA. Ozzy. It's a solution to the equation because there's a particular solution. Okay? So what we get is the V sub C particular is VA. That's it. So that means the total solution then is this, but I still got to solve for K1 and K2. Now, by the way, suppose you didn't like what I just did. Suppose like, oh, that math, I don't understand it. All right, not to worry. Come back here. I'm now on the screen. Forget the math. Go with your instinct as an engineer. I close the switch, constant input. I go out for a cup of coffee, I come back. What's the voltage across the capacitor? No, not zero. V sub A. Why? Because the current is the inductor is a short, the capacitor is an open. That means there's no current, so all that voltage must be across the capacitor. Okay? So the particular solution is a steady state. That's the key. So whether you get it by looking at the circuit or you get it by looking at the math, either way. Now, by the way, don't fall into the trap because the next problem I'm going to do is the same problem, but I'm asking you for the current. What's the current in steady state? Zero. Do you see why? Capacitor's open. Okay, so be careful. Don't get those mixed up. Okay, so my colleagues, I now have the solution. Now, I didn't say you had to solve for S, so don't waste your time. S, if you remember what it is, it's plus and minus, it's alpha plus or minus the square root of alpha squared minus omega sub 0 squared. It's a plug-in. You only got 55 minutes for this exam. In this case, I didn't ask for S, so don't go solving it. If I didn't ask for it, don't solve for it, okay? So we now say, great, I got the quote-unquote solution, but I got to solve for K1 and K2. Now, how did I, turns out do your best to determine the two constants, K1 and K2. Each constant should be expressed in terms of VA and S. All right, so here we go. We're in good shape. We're like a good part of the way through this problem. V sub C of t at t equals 0 plus is 0. I give you that. So apply it. V sub C at t equal 0 plus is 0. What did I get putting in t equals 0? I get K1 plus K2 plus VA equals 0. All right? The next condition is I at t equals 0 plus is 0. Now, for those colleagues who don't know this is a stumbling block. So here, I want to make sure you know this. I need a second initial condition on V. What are they giving me? A condition on I. I'm like, what the heck? I don't think I need that. You can use it though. Okay? So look, what do I know? I hear silence, but there's about 7 people I heard on the archive version just say CDVDT. So I equals CDVDT. That means that I at t equals 0 plus equals C dVdt evaluated at t equal 0 plus. We're good? We got it. We got it. So what can I now write? dV sub C of t evaluated at t equals 0 plus equals I at t equals 0 plus divided by C. How am I doing? We doing good? Now what's I at t equals 0 plus? 0. So C is non-zero, so this equals 0. So what I got is that the derivative of the capacitor voltage at t equals 0 is 0. That's great. That's my second initial condition. But do you see what I had to do to get it? We're good? All right, now, I'm going to keep this one. I'm going to erase this. Now, I need to take the derivative of this, because the initial condition is now dV dt. So, derivative of the capacitor voltage of t dt equals K1 S1 e to the S1t plus K2 S2 e to the S2t. V sub A is a constant, it goes away. How are we doing? All right. Thanks. So I say, great. So dV sub C of t dt evaluated at t equals 0 plus equals 0. That's what we were given. Now, how do I evaluate this at 0? K1 S1 plus K2 S2. I think this is pretty cool stuff. We're good? Now, I'm back on the screen. I'm going to slide down. Okay, here. Again, all of these exams are posted. Total solution, K1e to the S1t plus K2e to the S2t plus VA. We got it. Now, one equation, K1 plus K2 equals minus VA. That's that. Next equation, all the material we did here. K1 S1 plus K2 S2 equals 0. That's this here. So the rest, I have a couple of lines of algebra. Going back to the screen, substituting in, I can have you look at this on your own. You're all good. What we get is K2 is this, and K1 is this. Just substituting in and solving the two simultaneous equations. I'll let you look at that on your own. This is the hard part. If you get through this, you're in good shape. The rest is just now solving for S1 and S2. How do we do? Good, good, good. Okay, that's one problem I wanted to look at tonight. What I'd like to do now is go to the other version of the same exam and look at their second order system and show you the other way that I may ask you. So, my colleagues, I'm now on quiz 2, spring 2019, version 2. Version 2. All right. Now, problem 3, second order system. Now, part of me feels I only have to do the first part of this problem. We'll see. The first part, I think, is the part that's most different. So, same setup, same circuit. And now, I'm going to ask you for I of t. So let's read the problem together. Write the second order differential equation for the circuit above for the current. Note, the only variable that should be in your answer is I. So I say, good. We're now going to take a walk again. Always take a walk. And as you said, that's VA. So I get minus VA, very similar beginning, L di dt, plus, I guess I should have put R first, but it doesn't matter. R times, you know what, that's going to bother some people. Hold it, let me do this the right way. I'll get email Sunday night. R times I of t plus L di dt plus v sub c of t equals 0. All right, so now I of t is okay to have. V sub c is not. Okay. What I want is an expression that says v sub c equals something, and that something has I in it. What can I do? What do I do? Anyone remember? All right. I equals C dV dt. Okay. What I get is 1 over C I of t dt equals dV sub c of t integrated from 0 plus to t, integrated from 0 plus to t. I'm challenging you a bit. I'm not showing you it all step by step. You should be able to follow along. I want to see if you're with me tonight. All right? Cross multiply I of t dt, divide by c. I then have two opportunities here to integrate both sides. I get this. All right, we're good? I see someone shaking their head. How can I help? How do you think? You want to come down and help me? Come on. Come on. All right. Here. I'm going to say it. All right, tell you what. I'll write it out. All right, here we go. Come on. You can do this. I need feedback. Huh? All right, we're good? Now, I'm going to erase it in 3, 2, 1. Yes? Sorry? Did I do? I have to talk very loud. I remember my ears are covered here. You got to talk really loud. You don't remember me going through this in class? No, Kaylee. Kaylee. Huh? Kaylee, I did both. You see, Kaylee, do you see it in your notes? I'm going to have a note inspection, Kaylee. We're going to inspect your, you got it? Are we good? I know I went over this because this is a classic issue in second order circuits. I wouldn't have shortchanged you. Is your faith in me restored? Yeah. Okay, good. Will, thank you. Thank you. Sorry, Phoebe. Got to talk louder, Phoebe. Because I want to get rid of V. That wasn't a very convincing oh. That was I'll watch the video and I'll get it. No. Phoebe. Ah! By the way, am I going to get likes on this video? My son was crushed. Had 0 likes. He was like, all right, Phoebe, here we go. V. This problem says get rid of V. So what I want is V equals something I. What do I know? I equals CdV dt. So I do the opposite. So what I now get, with your permission, can I erase this? Phoebe, stop me if I'm not connecting, okay? You sure? All right, I'm going to keep going then. So here, the integral of a differential is a differential evaluated at the upper limit minus the differential evaluated at the lower limit. So what I now get is V sub c of t equals 1 over c. Hello. The integral from 0 plus to t of I of t dt plus V sub c at t equal 0 plus. Let me stop. It's important you got it down to here. Sir. I don't care how you say it as long as you can write it. How about that as an answer? It's not an oral test. When you go for your PhD, I'll give you an oral test. And that's when you got to say V sub c at t equals 0 plus. Until then, you're okay. You can just write it. All right, good. Anything else? All right. Phoebe, are we connected? So, Phoebe, what I now do is I take this. Where do I substitute it? Exactly, Zach. Right up here. Into this. All right? So let's do it. Da, 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 da. Okay, here we go. So this becomes 1 over C integral from 0 plus to t of I of t dt plus v sub c at t equals 0 plus all of this equals 0. Now, I'm now going to erase everything but this. We're getting there. How we doing? All right. So I'm going to erase everything here. Dun, 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 dun. All right. Is this second order? It is. It is. First derivative we used to call when I was in school was plus 1. The 0th derivative is 0. And then the integral was minus 1. If the first derivative was plus 1, the integral is minus 1. They're opposites. So we go from minus 1 to 0 to first. So we span 2 orders. Now, I'm going to get rid of the integral because I know how to solve a second order differential equation that doesn't have an integral. Okay? So what do? How do I get rid of an integral? Take the derivative. So, derivative of a constant. I'm going to move this over here. Derivative here. Ah. 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 This. Now this. R. Ah, what a beautiful symmetry. Got rid of this. What's the derivative of this? Just the integrand, right? Right? What's the derivative of this? 0. It's a constant. So, we're almost there. Is this standard form? Princeton would say no. Princeton would say no. We got to divide by L. So we divide by L. Second derivative, I of t dt squared plus r over L times di dt plus 1 over LC times I of t equals 0. That should now be the answer. Running back over here to the screen, all of this is worked out. di dt, this is the second derivative, plus r over L, di dt plus 1 over LC, I of t equals 0. How do we do? Sir? Talk a lot louder. Why do I integrate from 0 plus to t? Well, what would be a regular interval? Help me to understand your point. You're saying why not use a regular interval? What would that integral? What would that be? That's a beautiful thing, though, because it goes away when I take the derivative. Here's the answer to your question, and give me feedback. The question says, I want the equation for all t greater than 0. That means I have to integrate from right after when the switch closes, which is 0 plus, up to some arbitrary time t. So I have to integrate from 0 plus because the circuit is not active until I get to 0 plus. And I have to integrate for all t, so leave it as a variable t. I don't know how to make this simpler. If you do, let me know. We're good? Yes. Yes, you have to add the constant. Yeah, the constant, however, would go away when we took the derivative because it's a constant. I think it's the same thing. I think. I'm with you. You're good. You're good. You're good. We're good? All right. Now, my colleagues, there's a little part of me that says, I want you to do the rest of this problem yourself. Okay? So look, part B. Oh, does this sound familiar? Does this sound familiar? You're now given a second order system that's over there. Where have I heard this before? Here are the two initial conditions. Solve for K1 and K2. My colleagues, I'm going to let you do that on your own. Okay? And we have another question. Yes. Right. This is a very important point that you're raising. And I'm wondering if I forgot to do part C of the other problem, because there's a part C of this problem. So I'm making a little mental note. My colleagues, our colleague right over here says something very important. In this circuit, I've already answered this question, but I want to hear it from you now. In this circuit, as t goes to infinity, what's the current? 0. So what's the particular solution? 0. Now, suppose you didn't see that. Fair enough. Suppose you saw it, but suppose we didn't see it. The input's a constant. So that means the particular solution's a constant. Let's call it K3. Second derivative of a constant. First derivative of a constant. We then have the constant over LC equals 0. L and C are not 0. They're finite numbers. That means K3 must be 0. So in one case, the voltage over the capacitor went to V sub S. But as you're pointing out, the current went to 0. So if you get that, the particular solution is 0. Did we do good? Good. All right. Now, my colleagues, I think you can solve the rest of this yourself. Okay? I really do. It's a very similar type problem. However, I do have one concern. I think in my haste, here, this is the problem we did solve for the voltage. I did part A. I did part B. I did not do part C. Oh, let's go back and do part C. So I'm back to the other problem now. All right, I'm back to the problem we did first. The voltage, right? We agree? I'm back to the first problem. Okay. Determine the range on the value for C for the second order system to be overdamped. Ooh, what a cool question. What's the range on the value for the capacitor for the second order system to be overdamped? I'm throwing a outside curve on this one here. All right? I want to see how many people are going to swing and miss. You won't. You won't. You'll swing and connect. All right? So, what do we know? Overdamped, zeta is greater than 1. Now, what's zeta? Alpha over omega 0. What's alpha? What's omega 0? If you go to the formula sheet, tells you if you go back to part A, that the term in front of the first derivative is 2 alpha. So 2 alpha equals R over L. Omega sub 0, omega sub 0 squared is the term in front of the non-derivative, which is 1 over LC. So omega sub 0 is 1 over the square root of LC. Am I doing okay? Excellent. Thanks for the feedback. Now, what is zeta? Alpha. What's alpha? R over 2L. What's omega sub 0? 1 over the square root of LC. This has to be greater than 1. Do I have that written down? Zach, what do you think? You think I got it written down? Most likely. I would hope so. Okay, back to the screen. Here we go. R over 2L, 1 over the square root of LC, has to be greater than 1. Let me leave the rest up to you. Solve for C.
You missed all the good stuff.
No, I've done everything. Come here. Here, look. Step by step. It's all there. It's all there. So you got it. Just solve for C. Okay? And what you get is C has to be greater than 4L R squared. My colleagues, I got you down to here. I write it up step by step. The rest, I have no doubt you can do. Okay? The rest is just algebra. Solve for C, and you get C is that. Now we've done our second order system. All right? What's your confidence level on second order? You got it? Princeton. Got to talk loud, Princeton.
What would happen if you, in the question, you ask, instead of a v sub t, you ask for v sub l? Like, how would that change the problem?
If I asked you for V sub L instead of V sub C, how would it change the problem? What do you think? V sub L is L d I dt. Right? If you solve for I of t, take the derivative, multiply it by L, and you got V sub L of t. Right? So, in the other problem, I'm now over to the board here. The other problem, we solved for I of t. So, Princeton, the way I would do it, I'm sure there's other ways. Solve for I of t, which we've done. Take the derivative of that, multiply it by L, and that's now V sub L of t, because V equals L d I dt. We're good?
When you take a walk, so that means you, for the equation, you include v sub l of t instead of v c of t?
Yes, you could include V sub L of t.
Okay.
Okay, I would solve for I of t and then take the derivative, multiply it by L. That's how I would get V sub L of t.
Okay.
Did I do okay?
Yeah.
But when you take a walk, you're taking voltages, so you could write V sub L of t. We're good?
Yeah.
All right, good. All right, second order, done and dusted? All right. All right, now. Quiz 3. Quiz 3. Spring 2019. Quiz 3, Spring 2019. All right. There are 4 problems. Is real and reactive power on our exam? No. Is filter analysis on our exam? Filter analysis again? How about sinusoidal steady state? That's it, baby. That's it. All right. Now, you haven't seen this yet. Okay? You haven't seen this. So, think of like you stayed up all night and you got tickets and you're watching the first episode, right? The first release of this movie. You're getting an advance notice. Okay? But now let's do nodal using sinusoidal steady state. Okay? Consider the circuit shown below. How could I not consider it? Okay? Consider the circuit shown below. All right? So I say, okay, oh, by the way, I've already done the conversion for you to save you time. I try to be a good man. It might be, it might not be. If I'm in bad mood, I won't. Sir. Right, I would just keep the answer in polar form. Okay? So let's now read what the question is asking. Determine the steady state voltage V out. Hint, dun dun dun. Use nodal analysis. Another hint. You may wish to first solve for voltage V1 and then solve for V out. And to my colleague, please write your answer in phasor or what's called polar form. Zach.
Is it fine if we have a constant input of 10 volts?
It's not 10. It's 10 volts at a 0 degrees angle. Right? I have done the conversion for the omegas there. So the input is sinusoidal. It just has no phase angle. So it's 10 at an angle of 0. All right, we're good? Now, let's do it. Solve for V1. I think if I go to solve for V1, I'm going to ignore the node for V out for just a moment. So I see 2 nodes. I see V1 and Zach, I see ground. So, do I have any supernodes? Nope. Do I have any diamonds? This is one equation. So, let's write it. V1 minus 10 over 25 plus V1 over 20 plus J10 plus V1 over 50 minus J25 plus V1 over 10 minus J20 equals 0. Let me stop. I need you to take a look at this. I need confidence that you got this part. Will.
When, for your last term, V1 over 10 minus J20,
Right.
Could you write instead V1 minus V out over 10?
You can. You can. If I go back to the screen, Will is saying, can I write it as V1 minus V out over 10? Yes. But then, Will, I'll have to write another equation for V out. So in the hint, I was saying first solve for V1. I was trying to tell you, nothing wrong with what you said, Will. But I think life is going to be a little easier if we let that V out go for just a few minutes. Because we're going to use voltage division to get V out. A lot easier. All right? But what you said was right. Now, my colleagues, the rest is easy. But you're not going, trust me on this. You're not going to get it by sitting down and looking at my solutions and saying, that's easy. I got it. That doesn't work. You got to practice how to now do this. I mentioned this today, my 2 rules. Kaylee, I mentioned 2 rules. When I multiply or divide, has to be in polar. When I add or subtract, has to be in rectangular or Cartesian. Keep those 2 rules in mind, and we'll now go through the solving of this problem. Remember, multiply and divide vectors, they should all be polar. Add or subtract vectors, rectangular or Cartesian, however you want to call it. That's the secret. All right? That and taking your time. Now, let's go through this. Nice and slow, and we'll go through it again. At least we'll give you an overview. We'll go through more detail now. Now, the first equation on the board should match what I have here. Do we agree? Now, some of you know what a complex conjugate is. There's another way to solve it. You can multiply top and bottom by complex conjugates. If you know that way, that's beautiful. That's fine. Let me tell you how I do it. My way is like really simple, really basic. So let me slide down on the screen. Okay. My colleagues, I take it real slow. V1 over 25, 0.04 V1. Minus 10 over 25, which is minus 0.4. We're all good? Now, what do I have here? I have Cartesian in the denominator. No good. Make it polar. How do I convert this to polar? 20 squared plus 10 squared, square root. 22.361. How do I get this angle? Opposite over adjacent. So the arctan or the inverse tan of 10 over 20. 26.57. Right? Now you got to sit down and you got to do this. Don't just look at this. You now get here. Cartesian in the bottom. No good. 50 squared plus 25 squared square root. Arctan of minus 25 over 50. Are you okay? Zach?
How do you know that's in cosine or sine?
I'm sorry?
How do you know if that's in cosine or sine, the angle?
How do I know if it's in cosine or sine? That's already been taken care of if I gave you the J notation.
All right.
The fact that the input was 10 at an angle of 0 meant it was a cosine. So this is just getting angles. We're good? V1, 10 minus J, 20. 10 squared plus 20 squared, square root. Arctan of minus 20 over 10. Are we good? All of that equals 0. All right, now my colleagues, what do I do next? I have the 0.4 V1. Now, I have V1 over 22.361 at 26.57 degrees. What do? The reciprocal of 22.361 is 0.0447. How do I handle the degrees? What's the degree of the numerator? 0. Degree of the denominator? 26. 0 minus 26.57 minus 26.57 times V1. I do the same here. And I brought that 0.4 over to the other side. You should get this. Are you getting this? I sense a question. Are you okay with this one, this equation up here? All right. V1 divided by 22.361. Just take the reciprocal, 1 over 22.361. And how do I get the angle? Angle of the numerator minus angle of the denominator. Do that for all the terms. All right? And my colleague, I had a minus 0.4. I brought that over to the other side. Are we good? Come on, give me questions. Anything else? All right, now, I want to add everything. But adding everything, I want everything in Cartesian, in rectangular. All right, now here's the burning question I have for you. I think you all know how to do this. How do I convert this to rectangular? Sine and cosine, cosine, sine. Here. .04 V1, .04 V1. 0.0447 at that angle, that is 0.0447 times cosine of minus 26.57 plus 0.0447 times sine of minus 26.57. That gives me the J part. I need to be driven by your questions because if I assume you're not getting it, I'm going to waste your time if you're getting it. All right? Here. Real J. Am I on the board again, Zach? Good man, Zach. Now let's take the first term. 0.0447. 0.0447. And what's the angle? Minus 26.57. My colleagues, I'm under the assumption that you can now break this up into horizontal and vertical. If not, now's the time to ask me. Now, right this moment. Yes? Right. This is here. 0.0447 times cosine of minus 26.57. Do you see that? Whatever it is. That comes out to 0.04. Now, I need you to help me. What's this? Come on, I have a long ride home. I don't want to be crushed and depressed. I want to drive home ecstatic. What's this here? Right, 0.0447 times sine of minus 26. Do I have the right numbers? That's my only concern. Am I plugging in the right numbers? Okay. So that should give me minus J 0.02. My colleague, did I get your question? You do that for every term. You do that for every term. So we have how many terms? 1, 2, 3, 4. 1, 2, 3, 4. Now, how do I add? I add all the reals and I add all the J's. Amen. So I add all the reals, 0.04, 0.04 V1, 0.016. I add them all up, right? I add all the reals and all the imaginaries. So this is 0.04 V1, this is 0.04 V1, this is 0.016 V1, this is 0.02 V1. So if I added it up correctly, and I think I did because the people would have complained if I had it wrong, I get 0.116. Now add all the J's. I get 0.028. That's all multiplied by V1 equals 0.4. Now you tell me what I do next. Come on, I want to see if you're getting this. I like that. Okay? That kind of says it all. We just do one of these. Okay? So what I get is V1. I converted it to polar first. V1, I just bring it down. Now, if I hadn't converted it to polar, I'm hoping you would have seen we had Cartesian or rectangular in the denominator. No good. We'd have to make it polar. So convert it to polar, and now we get 3.361 at an angle of minus 13.57 degrees. And that's the answer, since I didn't tell you what omega was. That was your question, Zach. And you'll find that this is V1. And I said it was the answer, but I misspoke. It's not the answer. What am I looking for? The out. Way to go, Will. So, Will, let me erase this on the board over here. Does everyone agree how I drew it? Lends itself naturally to voltage division. All right? So what I get is V out equals minus J20 over 10 minus J20 times V1. Now, top and bottom have got to be polar. If not, Chloe, I'm stuck. All right? So what do? Minus J20. How do I write that in polar form? 20, negative 90. Now you're talking. Now, I don't know what 10 minus J20 is. It's in my notes. That's 10 squared plus 20 squared square root. It's probably 22 something or whatever it is. And then the angle is whatever it is. Let me Let me go back and look at it. It's 22.361. All right? 22.361. Will, I think this is a little easier. So now you got it. Now everything's in polar. It's a piece of cake. Multiply 20 times 3.361 divided by 22.361. We get a little over 3 volts. How do I handle the angles? Minus 90 plus a minus 13.57 minus a minus 63.43 minus 40.14. Ozzy, how we doing? All right. My colleagues, we've just done our first nodal problem. We'll do another one on Wednesday. How do we do? All right, we're good? Sir. Right, let me repeat the rules and see if I can help. When you multiply the numbers, add the angles. We still have one more problem if you want to stay. If not, you can leave. It's okay, but I want to do one more problem. The next step is if you divide the numbers and subtract the angles. Did I get your question? All right. So what have we done tonight? We've done 2 second order systems. Today in class, we did those 2 examples. Was it 3.5 and 3.6? Or 3.4 and 3.5? I forget what they were. I wrote them down. Right? That was good. Those are basic, like a ZEQ, and then we did voltage division. So we got those 2 problems done. So second order twice, and then those 2 in-class problems today. And then right now, we just did our first nodal. Okay? Next problem. Let's do mesh. And then we'll call it quits. Okay? Now, I was trying to find mesh in my exam. I guess it's been out of my rotation for a while. So maybe I need to put mesh back into the exam. So, sorry. I don't know. See, I could give you one from class today, voltage division, and a nodal. I can give you one from class today in mesh, or I can give you nodal mesh. And just think on the final, we got 4 hours. I am, Kaylee. I stumbled, though, Kaylee. All right, I'll go. Listen, I'll go easy on the final. I'll try. My easy may not be your easy, but I'll try to go easy. Now, Kaylee, I'm silly to bring up the final. Let's get the third mountain behind us, or the third hill. All right, so my colleagues, today in class we did 5.4, we did 5.5. On Wednesday we're going to do 5.6. You already know how to do it. Ah, let's do this. We'll do this, and I'll pack up the horses and get out of here. All right. Solve for I1, solve for I2. Now, the key thing I want to share with you about Chapter 5, I said it twice in each section today. Chapter 5 is like Chapter 2, except complex arithmetic. All right? So, plus and minus, this is now 100 at an angle of 0 degrees. I'm going to write down here that omega is 1,000. Now, excuse me. What's the reactance of an inductor? J omega L. So J omega 1,000 times L 0.1. This is J 100 ohms. We're good? Zach, help me out. That's the reactance. I hope I didn't say anything different. I might have said resistance by accident. Yeah, it's the reactance. A pure inductor, an ideal inductor, is a pure reactance. Now, we then have the resistance of 100 ohms. Now, they don't have ground here, but I'll add ground, Zach. We then go through the capacitance. Now, I don't have this in my head, but we'll see what we can do. X sub C is minus J over omega C. Minus J over omega is 1,000. Now, what's C? 5 microfarads. So if you don't mind, I'm going to look ahead at the next page, okay? I don't know what this is. It's 1,000. Can we figure it out?
Yeah.
5 times 10 to the minus 3, right? So it's 200, isn't it? I think it's negative 200. What do you think? Let's come on. It's a Monday night. Let's be daring. Okay. Minus J 200. Then we have another inductor. I'm putting ground, Zach, because you're my groundskeeper. You're the man. 0.1, same thing. J 100 ohms. Let me just peek ahead to make sure I didn't make a mistake. And then I'm going to, yeah. All right, we're good? Now, this is I1. We're almost done. This is the last problem, and we will have achieved our goal. I1, I2. Now, just like Chapter 2, except complex math. Hold on to that. So you know me, I start bottom left. So I'm going to take a walk. Minus 100 at an angle of 0 degrees. Now, by the way, do I have a super mesh here? No. Then plus J100 times I1. What's the next term? What do you got? Plus 100 times I1 minus I2. Bravo. And all of this equals 0. Do you got it? Do you see it? We're good? All right. Now, let's start up here. Come on. I want someone to give it to me. Come on. What do you got? Ozzy, take it away. Wonderful. Negative J 200. Go on. Ozzy, perfect. Keep going, buddy. Plus J 100. You got it. I2. Ozzy, go for it. Yep. You got it, Ozzy. Wow is right, Will. Way to go, Ozzy. You knocked it out of the park. Minus J 200 times I2 plus J 100 times I2 plus 100. Then it's I2 minus I1. I encourage you to solve these two. Princeton.
What's the rule again? To know how many equations there are for a mesh?
I would tell you for a mesh. The question is, what's the rule for knowing how many equations? I would tell you, on mesh it's a little tricky. So I would say solve for I1 and I2, 2 equations. Unless there's a super mesh, which I don't think I'll give you. Or a diamond, which I don't think I'll give you. We're good?
Yeah.
Solve these 2 and you did it. Complex arithmetic. You can do this. Done and dusted. How do we do tonight? Worthwhile? All right. Zach, should we sign off? Home audience. Gracias. Buenas noches. All right, the home audience. Yeah. All right, everyone. I'm out of here.